Hey guys, welcome back to another video. So today's video is going to be a little different from some of my other videos, and I'm going to be starting a new series called 3D rendering, in which I'm going to be showing you guys the process of rendering a 3D object onto a 2D screen, as well as maybe building it for ourselves in the future. So first, I'm just going to be showing, in this first tutorial, I'm going to be showing you guys the basics of it through this PowerPoint, showing you guys how it works, because it is quite a complex topic. So I'm just going to be using this PowerPoint to explain exactly how it works and how you can implement it yourself. So yeah, this is a title slide. Now, of course, we're going to need a bit of maths, since 3D projection is basically all just maths. Like, if we want to move a object in 3D, we of course need to apply some transformations to get into some 2D points. So we need to know about vectors. A vector is just a direction and a magnitude. So for example, this one, the direction is going to be well, in sort of a top left direction. You could explain it better with some angles, but you can really just think of vectors in this case as just a set of two numbers representing the x and y axis. And matrices are a set of vectors. So here this would contain a vector of a 3D vector of x1, y3 and z of 2. Multiply this by a transformation vector such as this, and you get a new vector. So yeah, we have some animations here. That is the translation of a vector, and this is the rotation of a vector. Okay, so now we're going to move on to rotation matrices. So if you go here, these are just matrices, except we use this specific formula which gives us a rotation matrice, and we can multiply this matrice by another set of points to give us those points rotated around the origin. So this might look complicated at first, but it's really just a formula, so you don't really have to worry too much about this. You can see Rx, Ry and Rz all represent different rotations using Euler angles. So for example, if we wanted to get the rotation matrix for 90 degrees rotation on x, 45 degrees rotation on y, and 30 degrees rotated on the z-axis, what we would do is we just use this formula, and that would give us this, which simplifies down to this, like that. So now we can actually start getting into the interesting stuff, now that we've got all this basic maths out of the way. There's different types of 3D projection. We have orthographic. So if we imagine this as the camera, and you can see these green lines represent rays of light. In orthographic projection, rays of light travel straight, so the distance the object from the camera doesn't really matter. This black screen is actually the viewport. It's effectively the screen here, so that's what it's representing. And you can see, since rays are always parallel to each other, even if the object was really far away, it would still appear the same size on the viewport. Now this is different to perspective, where the rays go towards the camera. This is 1 point perspective to be specific, and you can see we get this perspective effect on the viewport if we look at it from a different angle down here. And yes, we can see that the objects will actually get smaller as they get further away, because the rays will be coming in at a smaller angle, so it makes it smaller. There's one more thing we need to do before we actually get into the actual process of orthographic projection, which is what I'm going to be talking about today. So if we imagine this this blue square as the camera, this black square as the object, and this is its rays, the viewport, it's the rays of light that go towards it. If we imagine this as coming over here, then that is the same thing as the camera going here. We've just rotated everything about 45 degrees to the left, which is why, if you think about it, the camera is our viewport, is our point of view inside the world. So if we rotate this and rotate everything else, it's not going to change the actual effect that we see. So this is just one more thing to be aware of. Now we can actually get into the process of creating a scene such as this. So you can see this is a 2D image that we have here, but in our eyes it looks 3D because our brain is actually filling in the gaps and making this into a 3D sort of model. So I'm going to be showing you guys the steps of rendering this cube onto the screen in this 3D world. Here are the 5 steps of orthographic projection. Of course, perspective will come later, and I'll also be doing a practical demo, so be tuned for that. But yeah, here are our 5 steps. The first step is to get the object data. So what I mean by getting the object data is just creating a matrix of all of the object's points. Here you can see a cube, which is like similar here. I've just drawn it out a bit weirdly, but yeah, if we imagine each of these vertices as one of the points, and then you can see each of these columns represents one of the vertices. So this -50 on all x, y, and z is going to represent, let me think about this, it's going to represent this number 5 or number 1. I kind of forgot how the z-axis works. Actually, I believe it will be number 1, yeah. So this is actually going to represent point number 1. So that's all we mean by get object data. And in this squares, we're actually going to see the current appearance of, if we were to just render all of these points at the current moment, what would it appear like. So you can see right now we just have a bunch of coordinates. Since we're looking at this in 2D, we only render the first x and y coordinates, so we just have repeated 50 coordinates, which just gives us this square. Next step is to rotate the object. So in this case, our cube is going to be rotated -20 degrees in the x-axis, 20 degrees in the y-axis, and 0 degrees in the z-axis. We plug that into the rotation matrices formula I showed earlier, and we get this transformation matrice. Multiply this by the cube's matrix that we created in the previous step, and we get this new matrix, which contains the new points of the rotated cube around the origin. So now we can see the cube is starting to form in 3D space. All we're doing is rendering these first x and y coordinates, and we can see we're starting to see it. Next step is to translate the object. So what I mean by translating the object is just moving it. In our example, I believe the object is at position 200, 0, 0, so 200 on the x, 0 on the y and z. So all we do is we literally just add 200, add the vector 200, and if you know how to add a vector plus matrix, you basically just add 200 to each of these columns, which gives us this. So now we can see all it's done is just move the cube over there. Translate world step is basically the same thing, except we're translating it based on the world's position. So what I mean by that is in orthographic projection, the camera is still there, of course, but it's not as important as in perspective, because the distance from the camera to the objects, and even the angle to some extent, doesn't matter too much. So I tend to think of it in terms of the actual world rather than the camera, which is why I can just say translate the entire world. In our case, the world is not translated by anything, so it doesn't really matter, but you can see we're adding a 0, 0, 0 vector, which is just going to leave it the same, so we get the exact same image. The final step is to rotate the entire world, and this is what I mean. So you can either rotate the camera angle, but I think it's easier to think about it as rotating the entire world. So in our example, I'm actually going to rotate the world by 20 degrees on the x, minus 20 degrees on the y, and 0. And if we apply that to, if we put those numbers into the rotation matrix formula from earlier, we get this transformation matrix, multiply that by the matrix which we've been building up to this point, and we get our final matrix. And this is actually the final vertices of the cube. So of course, to get these faces I had to do some extra things, but that wasn't too difficult. We just had to join up the vertices and color them in, and we see the world is actually being rotated fully. So these grid lines have been rotated, so now we can actually see the z-axis, and so is the cube. And that leaves us with our final image, which is this, as you can see from here, which is the image we were looking for at the start. So yeah, there's some applications to this. We can be used in CAD, animations, cinematography, as well as video games. So yeah, that 3D rendering is really useful, and I'm actually going to be showing you guys a practical demo of a 3D engine I built a few months ago in the coming videos. So you should be able to see this kind of work in action, as well as showing you guys a demo of a perspective visualization, and maybe in the future I'll even build a 3D engine, because it's actually quite simple once you understand these 5 steps. So thanks for watching, and I'll see you guys these 5 steps for orthographic projection. Sorry. Thanks for watching, and I'll see you guys in a future tutorial. Bye.